Okay, first I want to extend my thanks for being invited here. It's an honor to speak in this venue, and I thank you all for coming and listening to us early in the morning. So, or at least to us Americans, it feels like early in the morning. My talk we'll be looking at the similar kinds of questions that Nathan just talked about, looking at the large-scale structure of the Earth's lower mantle. But the approach that we will be taking is to try to identify those features in the set of global tomographic models which we should believe to be robust, to be truly representative of actual Earth structure. And this is work that's collaborative in nature, so it spans a number of different institutions, and here are my wonderful co-authors. So here's just a summary slide of what a reasonable view of the large-scale mantle seismic structure should look like. This view is based on long period shear velocity models, so there's that caveat. And if you just what we can do is we can take a modern global tomographic model like S40RTS of Ritsema et al. We can plot it at a variety. We can plot its variations in shear wave speed at different depths. So here it's shown at 100 kilometers depth. And we can look at it in this spatial scale, or alternatively, we could look at the power at various spherical harmonic degrees and look at the models in the wave number domain. But either way you look at it, the models pretty much divide up the Earth into 4 or 5, depending how you count, zones. So if we start from the top, at the top we have a very strong level of heterogeneity, so we call this region the heterosphere. Here the lateral variations in VS are on the order of plus or minus 10%. The signal is dominated by the signal arising from the fast continental routes and the slow mid-ocean ridges and subduction zones here. If we look even just a little bit deeper, so this is at a depth of 300 kilometers, this signature is completely gone. The world looks very different 300 kilometers down. The spectrum looks very different. In the wave number, the models look very different. There's no longer this very dominant peak at degree 5 that represents the ocean continent function. And then if we look further down into the transition zone, the world changes yet again. Here we have these very fast regions beneath, well, they're 2% fast, but they're certainly, for this depth range, they're very fast. Regions beneath the Western Pacific and beneath South America, which are locations where we have the accumulation, perhaps, or the laying down of slabs that have been subducted in the Western Pacific and beneath South America. The signal, once again, looks different in the wave number domain as well. We have a peak at degree 2, which comes from this subduction signal. There's also some slower than average signals throughout, which are fascinating, and I'm sure you'll hear more about over the course of the next few months. So in the upper lower mantle, we have a very white spectrum, so there's a heterogeneity at all length scales, and then as we go to the base of the mantle, we have a unique pattern of 2 extremely slow, large, low shear velocity provinces. This is the Pacific one and the African one, and then they are surrounded by a ring of faster than average, but really barely faster than average velocities. And this is at this depth range, the degree 2 structure dominates. So this is kind of the large-scale view of the mantle. And we can look at more detail. We can look at a number of different tomographic models. And here I'm plotting the model of S362 ANI of Kustovsky et al. So this is the latest Harvard model, plotting the S40RTS Ritsema model, the Romanowicz SAW24B16 model, the HMSLS Hauser et al., so UCSD model, the gypsum model that Nathan just talked about, although I probably have a slightly older version of it. This is all plotted at the base of the mantle, so at about a depth of 2,800 kilometers. And you can see that all these models show very similar structures. The one kind of clear difference between them is that the S40RTS has a slightly lower amplitude of anomaly, but this is actually due to the parameterization of that model and is not representative of an actual difference in the structure. In this model, the lowest most splines are taller, and so they average the structure with the overlying structure a little more than the other models do. But in general, we see again these two large low shear velocity provinces, and in fact these provinces can be seen directly in data. So this is SCS and SDiff data from Urshka Manner's thesis, and you can see here the residuals are all slow, and this corresponds to the LSVPs, and then it's surrounded by a ring, a circumpolar ring of faster than average regions. Okay, so great. So we can look at these maps, and so what? We talked, actually Nathan's talk was kind of a nice introduction to my talk, so thank you, Nathan. And these models are all constructed with different parameterizations and different regularizations and different data selections and different theoretical formalisms. And so these differences that we see, even though there's a lot of commonality in the structure between them, if you look at detail, there are differences between these models. So the idea that we are working on is that differences in these in the parameterization, regularization, data selection, and so forth will produce differences in these models, and then the structures which are common to all the models should be structures that are unlikely to be, one, in the null space, and two, result from artifacts of the theoretical approximations. So let's take a look at how these global VS models are constructed. Here you really have to go back in the papers, and then you notice all the things you forgot to put, or the other authors forgot to put. Some of the models are parameterized. So this is the physical parameterization as opposed to the all these models are inverting for shear velocity perturbation. So some models are parameterized in spherical harmonics, some are in spherical blocks, some are in other kinds of spherical blocks, and some are in spherical splines. They have different numbers they're parameterized differently in depth. They have different sets of data. Some use only travel time data, some use surface wave data, some use full waveforms, some use a combination of the two. There are differences in the theoretical framework which might be very important. And finally, there are differences in how the models are smoothed, whether you are using norm damping, whether you're using first derivative smoothing, regular smoothing, and so on and so forth. So what we, well, you know what, let's just skip that. So a way that we can compare these models, okay, well, I can show this. Okay, so a way that one might compare these models is to compare their spherical harmonics coefficients. So here I'm showing the spherical harmonic coefficients for degrees 1, 2, 3, 4. So you're going to shorter wavelengths to the right. So you have very long wavelength structure to the left at a variety of depths in the lower mantle. And so you can see that all the models have very similar spectral content at the base of the mantle, and then these differences kind of increase slightly. There's also these very characteristic patterns. For example, this pattern of the L equals 2, which is a kind of a recumbent L equals 2 aligned on the equator. And this pattern persists more than 1,000 kilometers up from the core mantle boundary. The degree 3 pattern is also characteristic and continues through. But, you know, I don't know about you, but to me this is not obvious how to interpret some of the similarities or differences in spherical harmonics coefficients. So there's a technique that allows us to compare the differences between these models, and the technique is a very standard data analysis technique, which is cluster analysis. So what we can do is we can take the profiles of velocity in any depth range in the mantle. So here I'm showing profiles in the upper 350 kilometers of the mantle. And we can group them according to how similar they are to one another. And then we can define an average profile for each family or cluster or group of profiles. And we can also look at where these families of velocity profiles, what their geographic extents are. And so we can make a map here. So this is the result for the upper mantle, where if you do this kind of clustering and you allow 6 groups, so you divide the data objectively into 6 groups, and the reason I say it's objective is because you're minimizing an objective function when you do this. So you divide up the Earth into 6 regions. The young oceans, the middle-aged oceans, the old oceans, and then the cratons here, the stable platforms, and then the tectonically modified portions of the continents. And so what's nice is that cluster analysis is objective in the sense that you are not yourself choosing what is similar to what, and also it seems to be kind of meaningful, because if you look at how the geographic extents of these clusters change as you increase the number of clusters, they progress in a very sensible way. So when you divide up Earth structure into 2 regions, you get the ocean-continent dichotomy. If you add a 3rd region, you separate the young oceans from the old oceans. A 4th region allows you to bring out the portions of the continents that are tectonically modified, and so on and so forth. So there is it seems that the results of in the upper mantle, the results of cluster analysis are interpretable in terms of tectonics. And so what this allows us to do is we can create a map, a regionalization very akin to the regionalization here of that could be done, for example, based on the ages of surface exposures, or based on heat flow, or however you want to do it. And because for each region we can define an average VS profile, these average VS profiles summarize the information content from the models in some way. And also the similarity between the geographic extents of the regions defined by different models tell you how similar the tomographic models really are. So what happens when you do this in the lower mantle? So here I allow the formation of 2 clusters in the lower mantle, and I'm analyzing 5 different models. So if you do this clustering, so you group all the profiles that look similar into within 2 groups, you get and you plot the geographic extents of those groups. Then the cluster analysis divides the world into two regions. One is a ring of faster than average velocities that kind of goes around these 2 large low shear velocity provinces, the African and the Pacific one. So here you see the integers, you have numbers from 0 to 5. So this represents the number of times that, or for a given location, how many models voted for that location to be in the slow cluster. So where you have 5s, where everything is right, it means all models agree that this location has a velocity profile which is characteristic of the slow cluster. And then in the blue regions, it means that no models thought that. So there's remarkable intermodel consistency. In fact, even if you look at the edges of these LLSVPs, you see that the models agree for example, here, all the models agree this point is in the LSVP, and all the models agree that it's not on this side. So this allows us to define these boundaries of the LSVPs. In fact, the boundaries of the LSVPs are known to be quite sharp. So if we look at, we can look in detail at these boundaries by doing waveform analyses, and this has been done in a variety of regions by a variety of different authors, and they have found in all of these circled areas evidence for very sharp transitions in velocity. So from going from a very slow region to a slightly faster than average region across small horizontal length scales. So the fact that the edges of the LSVPs are consistent across models is nice, of course, but the fact that it's consistent with the locations that are inferred from waveform studies is even nicer. So now let's look at the average VS profiles within these models. So here I'm showing the deviation, so delta VS over VS in percent from Prem. And this is, these curves here are pertaining to the fast clusters. So this is for these blue regions. And then these curves here are for the slow clusters, so in the red regions. Okay, so it's the average VS profile within each of those clusters. So we can see that the average VS profiles of the two clusters differ by more than 0.5% up to 1,200 kilometers or more above the CMB. Okay, that's one observation. Another thing you might notice is that the differences between the slow and the fast clusters tend become very large very quickly, starting at about 2,200 depth of 2,200 kilometers, so about 600 kilometers up from the core mantle boundary. And in fact, it is not the fast clusters that are deviating from Prem, but rather the slow clusters are the ones whose behavior changes very quickly. So in these slow regions, when the velocity deviates very quick, starts to deviate abruptly at a 2,200 kilometer depth, and the deviations can be quite large. So this is on average for that entire red region. It can be more than 1.5% slow with respect to Prem. And so when you look at this observation and you combine it with the fact that we know that the LLSVPs are bound in certain locations by very sharp lateral gradients in velocity, and with the observation of the anti-correlation of bulk sound speed and shear wave speed, these results certainly can be taken to be consistent with compositional heterogeneity. I just want to point out that this 1.5% difference in the average profiles of the slow regions versus the fast regions has some important implications for mineralogical interpretations of 1D profiles of the Earth. So here I'm showing the predictions from Matas et al. Of the, this is a difference of VS from AK-135 model, but really it's just a difference reference, between a pyrolytic, chondritic, and what they're calling a cosmic composition. And my point with showing this figure is that at the base of the mantle, about 1%, 1.5% difference in velocity spans the entire range of compositions. So this means that if, well, this goes back to this question of whether you want to throw all your, as much heterogeneity as you can into temperature, or whether you want to throw as much of it as you can into chemistry. And if you want to throw it all into chemistry, you can. Of course, this doesn't vary. You can vary more things than just these kind of large compositional suites. And the another way that you might try to explain these various properties of the lowermost mantle is to invoke the perovskite to post-perovskite transition. So what happens when perovskite transforms to post-perovskite is that you increase the VS and you reduce the bulk sound speed. So if you have post-perovskite present in the fast regions, then this might explain the anti-correlation of the shear wave speed and bulk sound speed, as well as the sharp lateral variation. But if you look back, if you look up at this, the average profiles of velocity, you see that the differences between the slow and the fast clusters start at about 600 kilometers up from the CMB. So at the very least, you need the post-perovskite to be present about 500 kilometers up from the core mantle boundary. And this may or may not be a problem. I'm not a mineral physicist, but recent experiments that were done by Grocholski and collaborators, which include the effects of aluminum on these perovskite to post-perovskite transitions, find that in a pyrolytic composition, in fact, the perovskite to post-perovskite transformation does not even occur above the CMB, and in a Harpsurgitic composition, it's barely above the core mantle boundary. And in fact, only in a Morb-like composition do you have the transition from perovskite to post-perovskite occurring a couple of 100 kilometers up. And even there, it's not obvious that it's high enough above the core mantle boundary. So that's one observation that perhaps the mineral physicist could tell us more about. And the other one is that what we see that this difference between the slow clusters and the average, so in the PREM, means that it is PREM, in the PREM model, in the 1D profiles that we've already been interpreting, the effects of post-perovskite are already in there. So if the PREM profiles can be made to be consistent with a perovskite to post-perovskite transition, then everything's fine. But if not, then you might have to move away from this way of interpreting the differences. You can also look at the distributions of velocity in the fast and the slow regions, and this might allow us to infer something about the temperature variations between the two in a way that's independent from the ways that have already been done. And you should stay tuned for Jan Matas's talk later today on this topic. So let's see what happens as you include shorter and shorter wavelength structures. So if you allow only degree 2 structure, and you do a cluster analysis, you get something very obvious, which is a degree 2 structure. But as you start to include more and more higher wavelength features of these models, and you look at the geographic extents of the clusters that you create, you see that the shorter wavelength structure really exhibits itself as an undulation on the borders of these large low shear velocity provinces. It's not that you get holes inside them or you get spots in the other region. It's really that the borders of these LLSVPs start to undulate. And things look pretty similar even if you include 3 clusters, so it's not just a special result that happens when you have 2, but that's perhaps not so interesting. What happens in the upper lower mantle? So what happens in the region from 800 kilometers depth to a region of around 1800 kilometers depth? What if you do a cluster analysis in this intermediate depth range? Well, if you do that, you get the following, depending on how you define the distance metric between the different velocity profiles, you get slightly different answers. But so in general, though, you see the slow cluster appears still above the African LLSVP and above the Pacific LLSVP, but it's become now much more fragmented and much more spatially distributed. Interestingly, whereas one can make the argument, as many have, that the location of the hotspots, which are here shown in circles, are preferentially found on the edges of the LLSVPs, as seen in the bottom of the mantle. If you look at the locations of this cluster in the mid-mantle, this relationship is much less clear, and it seems like the majority of hotspots you can place well within the slow cluster in the mid-mantle. But if you were observant, you might have noticed that there was in fact one exception, and only one exception, to this neat separation of structure between these 2 slow regions and one faster than average region, and this anomaly here is centered approximately beneath the city of Perm, so we call it the Perm anomaly. And it's interesting because it's small, but it's present in all the tomographic models, so also in Nathan's model. And it's the one exception to this neat separation of structure. So what is this anomaly? Well, it's different than the ultra-low velocity zones, where which are about 10 kilometer tall, about 100 kilometers across. Of course, these numbers are variable, but they tend to be dense and slow, so there are more than 10% reductions in VS anomalies. And they might be found along the edges of the LSVPs. Here's a figure showing that from McNamara et al. But this Perm anomaly is far bigger and far taller than these guys, so it's not really like an ultra-low velocity zone. In fact, what does this anomaly look like? Well, it's roughly circular in shape. So here it is contoured in the S40 RTS model. It's roughly circular in shape. It appears to extend about 300 to 500 kilometers up from the core mantle boundary, and it's not connected to the African LLSVP. This is, you can see that's all the models agree it is not connected. The profile of the distribution of velocities in the Perm anomaly, they start to deviate from Prem at about 500, maybe a little more kilometers above the core mantle boundary and persist to deviate from it at depth. We can look at the horizontal gradients. We can map them across the base of the mantle. So what we're doing is we're looking at a given location on the Earth, what is the largest velocity difference within 5 degrees or within 10 degrees of that location. And then you do this in all the models, and you take the median so that you have a robust estimator of these gradients. And you see here that if you plot up the gradients at the base of the mantle, all you really see are the edges of the LLSVPs, and they come out quite beautifully, and this circle around the edges of the perm anomaly. I want to point out that in the fast region, in the faster than average cluster, this is the cluster which is people tend to associate with the accumulation of past subduction, of slabs subducting in the past. These gradients, at least on the length scales as small as 5 degrees, are simply minuscule. So there's very little variability in velocity within the fast region, really strikingly little variability in velocity within the fast region. Okay, so this anomaly is so small, in fact, that we might want to consider wavefront healing effects and be a little concerned about it. The wavelength of 20-second S waves near the core mantle boundary is about 150 kilometers. This perm anomaly is only about, its radius is only about 3 times the wavelength. So it's really shocking that a slow anomaly, and so here's a figure from Malcolm and Trampere paper, which shows that when you have wavefront pass through a fast anomaly versus a slow anomaly, with the slow anomaly, eventually the wavefront will heal. This is a well-known effect, and what will happen is that this wavefront healing effect will mask the true amplitude, the true travel times caused by passing through this anomaly, and this is from a figure of Nollet and Dahlen. So the fact that we see this anomaly in all 5 models, and it is a slow anomaly, is really remarkable, because in fact, if it were a fast anomaly, it would be less surprising, because the wavefront healing effect does not work very well for fast anomalies. But for slow anomalies, it works quite effectively, but it does not manage to hide this anomaly from us. So we can then, if we become skeptical, we can start looking at the actual waveforms. So these are transverse component velocity waveforms in the 91 to 102 degree epicentral distance range. So these are S and S diff waveforms. And what we're showing is for this deep event that occurred underneath Spain across a variety of stations in Asia, we can, if we compare the observed amplitudes to those predicted for this earthquake, we see that there is a large increase in the amplitude of the observed waves versus the predicted waves. So this is due to the waves focusing as they go through this low velocity anomaly. And then in the travel times, we see a delay at this same time, and this is due to the fact that they're passing through a slow anomaly. We do not see this behavior further to the north, confirming that this anomaly is separate from the African LLSVP. And so what we can do, and this is work done by Sana Kotar, we can do forward modeling using the spectral element method. We're using the sandwich version of Capdeville et al. And we can vary the size, so this is the radius and the shear velocity reduction within this anomaly. We can look at a variety of different forward models, a variety of different possibilities, and in black we're shown that here are the data, and we can see that, well, if you look in detail, you can see that an anomaly that's somewhere between 300 and 500 kilometers tall and 700 to 1,000 kilometers across, with about a 6% reduction. If it's 10%, the waveforms don't look the same, and if it's 3%, the travel time reductions are not enough. So it seems that this anomaly is about 6% slow and about 300 to 500 kilometers high. So this perm anomaly is really more, you can think of it as a mini LLSVP, because it has velocity reduction similar to those seen in LLSVPs. It has sharp horizontal lateral gradients bounding it, but it's far taller it's far too tall to be a ULVZ, and has far too small a velocity reduction to be an ultra-low velocity zone. So it represents some new class of lower mantle anomaly, And the fact that we only see one and that it's slow and we don't see any that are fast might have some interesting implications for the nature of heterogeneity at the lowermost mantle. So thank you for your attention, and I'm happy to take questions.